Welcome, everybody. There are only three key and fundamental science questions at NASA that drive all research and exploration undertaken and funded by the agency. They are, number one, how does the universe work? Number two, how did we get here? And number three, are we alone? Of course, the third question is most closely associated with the SETI Institute, but we also have astronomers and physicists and planetary scientists working on question one, and astrobiologists, chemists, biologists, geologists, and others working on question two. Understanding how we got here perhaps starts with understanding the concept of habitable worlds, expressed in the Drake equation, which you all know, as N sub E. Of all the planets, how many are rocky Earth-like worlds in the so-called habitable zone of their host star? The next Drake equation variable is F sub L. Of those potentially habitable worlds, how many have the conditions necessary for life to emerge? And what exactly are those conditions? Tonight, we welcome back two very special guests to the SETI Talk stage who have devoted much of their scientific research to the topic of origins of life. How does life begin? How did we get here? Indeed, they have proposed a new word, urability, as a way of expressing the conditions that allow life to begin. Think of habitability as a world potentially able to support the onset of life, but not necessarily having all the right conditions, while urability describes a habitable environment where in fact the conditions are just right for life to emerge. Our guests will be introduced this evening by Franck Marchese, Senior Astronomer at the SETI Institute and the moderator for tonight's discussion. So good evening, ladies and gentlemen, and SETI Institute friends the world over. Thanks for joining us for tonight's SETI Talk, Urable Worlds, Where and How Can Life Start in the Universe? I'm Bill Diamond, the President and CEO of the SETI Institute, and delighted to have you all here, some in person and the rest virtually. In addition to this fascinating and entirely relevant conversation, tonight marks a very special occasion as the first return to live and in-person SETI Talk events since the onset of COVID pandemic back in March of 2020. So I'd like to extend a very special welcome to our in-person guests, the thousands of you who braved the cold and the dark to come and join us tonight here at the SETI Institute. Tonight's talk is also coming to you live from our brand new headquarters in Mountain View, California, where I personally invite you to come and visit, but just not all at once. For our regular SETI Talks attendees and new guests joining us via Zoom tonight, let me remind you that you can post questions that we will get to after the moderated discussion using the Q&A feature at the bottom of your screen, and we'll do our best to address as many of those as we can at the end of the panel discussion. I also want to remind you that we love to know where you are joining us from, so please use the chat function in Zoom to tell us in which, hopefully, Urable location you find yourself on our beautiful planet. Our SETI Talks lecture series is a production of the SETI Institute here in Mountain View, California, and it's made possible by the generous support of people like you. So learn how you can get involved in our mission, support our work, or sign up for our weekly newsletter, Journey, by going online and visiting us at www.seti.org. Tonight's talk is sponsored by the many donors and friends of the Institute who fund our research programs through their generous gifts. Their gift to us is a gift for all of you, as we are very grateful for their support. If you'd like to personally sponsor a SETI Talk or learn more about how to support our work, visit us at seti.org or contact us by email at info@seti.org. Before turning the podium over to Franck, let me tell you briefly about our next SETI Talk, which will be on December 14th, where Franck Marchese will once again be hosting us, but he will be live at the Space Telescope Science Institute in Baltimore, Maryland, for the very first science conference of the JWST mission. He'll be joined by some very special guests, so be sure to check our website for updates and details on that event. And with that, it's time to turn the proceedings over to Franck for our conversation about urability, the conditions necessary for the origins of life. Franck?
Thank you. Thank you very much. Thank you, everybody who is here today in person and people online. I'm very excited to see you both again. I think we had a SETI talk 5 years ago, 4 years ago? No, maybe 2? Oh, wow. Forget it then. But let me introduce you first. So the sound is getting bad. Okay. Dave Deamer. How are you? So you're a biologist, research professor of biomolecular engineering at University of California, Santa Cruz, not far away from here. You have been working in the field of biology for several decades, and you're one of the authors of a book that I really like called Terrestrial Origin of Life Hypothesis. So thank you for attending, for coming today. And on my far right, we have a multidisciplinary scientist, Bruce Deamer. Hi, Bruce. Also at UC Santa Cruz, you're associate researcher in the Department of Biomolecular Engineering. And both of you are going to give us a description of a new concept, urable words. It's a word that I learned this morning, this afternoon, how to say, and I'm sorry if I'm gonna butcher it quite often, but please take the floor and tell us a bit more about this new hypothesis.
Great. Okay, Bruce and I are going to have a conversation up here. You're going to be invited into the conversation as we go along. And the conversation is, we limit ourselves to 5 slides each. And that is tough, but it made us think about having a conversation. So I'm going to just start off to say that you're going to learn some new things from tonight. One of these is this new word that you referred to, urability. You're going to understand what that means. You're also going to learn something that I learned just literally a few days ago. My colleague at UC Santa Cruz, our Francis Nimmo and Joel Premack, and I had a conversation with Joel just yesterday, trying to get ready for this, because these two guys, along with Sandy Faber and one of our students, have come up with something that fits into urability. And it was unexpected to me, and I think you're going to be quite surprised about this. It has to do with neutron stars. It has to do with the fact that heavy metals like the gold in my finger ring, like uranium, like thorium, are made when neutron stars merge. Lots of things happen. You're going to find out that volcanism is part of the story that we're telling now. And the reason for that is we had to have some dry land on the early Earth if we're going to go through a process called wet-dry cycling. Because if you've ever been to a volcano, and I've been to half a dozen in my life, you notice that the water comes, it rains or it splashes, and then it evaporates. Something happens during evaporation that adds chemical energy to any molecules that are dissolved in that water. That chemical energy is called a condensation reaction. Out the other end come nucleic acids, and you are going to hear a little bit of our research results. And by the way, everything you're going to hear from Bruce and me, except toward the end, are laboratory based. In other words, these are experimental approaches. So we're pretty confident about what we're going to be telling you. And finally, we're going to startle the SETI people here, because we're going to challenge one of the fundamental exercises, one of the fundamental assumptions of SETI, and that is that there's someone else out there. We can make an argument that maybe not. So you're going to hear that toward the end. And I want everybody then to try to convince me that we might not be right, because as scientists, we're often wrong, that this is just an idea that emerges when we deal with urability. Bruce?
So to get started, I want to dedicate this SETI talk to the work and the memory of Frank Drake, whose memorial service will be 2 days from now. And hopefully many of you can join in with the celebration of this great man's life. So Frank came up with, of course, the famous Drake equation. And as was mentioned previously, the FL term, the fraction of suitable planets on which life actually appears, is what we are now calling an urable world, a world that can start life. And Dave's going to give us a simple example.
Now, here's a little thought experiment. We're going to reproduce what Louis Pasteur did in the 1800s when he demonstrated something that was not known until he showed it during a lecture, just as I'm doing here. He started out with a flask filled with nutrients. So everything needed for life to begin or to eat this stuff is in that flask. Now what we're going to do is to add one living cell, an E. coli cell. Come back 2 days later, and we discovered that that flask was habitable. By the definition of habitability, it had liquid water and it had nutrients as an energy source. So that was a habitable condition. But what if I did not add that bacteria? 1 billion years later, it would still be sitting there. Something is missing to allow life to begin in that flask. This is what Louis Pasteur said. He said, all life comes from life. We're going to tell you something different, of course, but that was his demonstration. And I think it gives you a really good idea of what the difference is between habitability, which is just a habitable zone where liquid water can be on a planet, and urability, which is a combination of multiple factors that allow life to begin. And keep in mind, if life cannot start on a planet, it will never reach intelligent life.
So urability is a combination of conditions and locations which can allow life to begin. And amazingly, in 1871, nearly 150 years ago, Charles Darwin penned a letter to his friend J.D. Hooker, who had asked about how could life begin. And he wrote this very famous little phrase about warm little ponds with all sorts of ammonia and phosphoric salts, light, heat, etc., etc., present that a protein compound was chemically formed, and it goes on to say, ready to undergo more complex changes, and that life couldn't start again today on the earth because it would be consumed. So what he's talking about is the urable conditions, and that the life earth today is inurable because there can't be a second Genesis. About 40 years ago, these amazing structures were discovered in the bottom of the ocean at hydrothermal vents, at fissure points between tectonic plates. They were predicted and then discovered with the submersible Alvin, hydrothermal vents forming these chimneys and towers. And a colleague of ours in 1982 proposed that perhaps life could start at such a place because it had chemical energy, gradients, structured pores perhaps in these rocks, and a potential spot on a planet where life can begin. However, in the last 35 to 40 years, the fundamental precepts of this scenario have never been shown, which is the fixing of carbon into more complex organics. It's never been demonstrated to the colleagues. So basically, much of our field and origin of life has moved back to Darwin's little ponds, back to subaerial volcanic landscapes, with a number of sort of paradigm shifting articles and debates in the New York Times and in Nature and Science and Nature magazines in the last few years. In the middle of all of this, Dave and I proposed that hot springs, a kind of vent on the land, would be good alternatives. Now, as a result of this, at our previous SETI talk in 2017, Jill Tarter was in the back row, and she stood up and said, well, can life start on icy moons? And Dave's response at the time was, we don't think so, because the conditions aren't there to start life. It may be habitable, but it may be a sterile environment. So next we'll go into the factors.
Salt water and fresh water. This is supplied by precipitation. This is our ocean 50 miles away. Salty water, it has half molar sodium chloride. It's got 50 millimolar magnesium, got 10 millimolar calcium. It's hard water. And as a biophysicist, that tells me a lot. Hard water causes soap to precipitate. If you try washing your hands in ocean water, it's not going to work very well because the soap isn't very soapy. And as a biophysicist, which is my field, I knew that membranes would have a hard time forming in salty seawater. So I began to explore the possibility that there's an alternative to seawater. And that is the water, the distilled water, distilled from the ocean that falls and feeds into these hot springs. So Bruce and I got together about 10 years ago now, and we've been pursuing the alternative as a weight of evidence. And that's an important term. This is the way science works. You are, if you were a scientist and I was a lawyer, I'm going to try to give you a weight of evidence supporting one idea. And then somebody else got up, another lawyer type, and tried the weight of evidence of the opposite. Well, for me, this is the one that I'm now arguing for. I think the weight of evidence supports this. And that's what we're testing in the laboratory. We're also going out into the field, and you're going to see some of our work from field work on sites like this. So I answered Jill because I thought it was implausible that life could begin. It could be habitable. If life ever got there somehow, it might be able to live on Enceladus in that liquid ocean, but it probably couldn't begin there.
So in our paper was published in Astrobiology Journal in July, we developed these factors for geochemical factors, combinatorial factors, and geophysical factors that would overlap, that have to be in combination to create what we call Urable centers, places through which prebiotic chemistry can go, can move. And the challenge we have in our field is there's so many overlapping factors. So we developed this visible language of strips to allow our colleagues a language to apply to what we think of Urable zones on worlds. And Dave will explain how that works.
Yeah, so some of this is obvious. This vertical stripe goes from boiling to freezing. Life cannot go anyplace in ice. There's very real reasons why, ice is used to preserve life, but it cannot grow in the icy environment. And life can get pretty close to boiling in its temperature range, but there is a limit, an upper limit. And an Urable center is someplace in the middle between these two extremes. The same is true for dry and wet, and for having light present or in the dark. All of these combine to produce an Urable center. These are just some of the ions that are in the ocean and are in our bodies. In fact, iron chloride, magnesium chloride, sodium chloride, calcium chloride. They can go from saturated to dilute. And again, there's some Urable center that allows life to begin when it could not begin in saturated calcium chloride, for example. So that's how we're developing these factors and combinations. Now, there's one more that I want to tell you about.
Well, this is actually an example of
Oh,
the
yeah, go
first
ahead.
Urable chart developed in a paper, and it was in a master's student who's working with us at the BIOTA Institute. And she actually took the Urable framework and used metal cation concentration to simulate conditions on Mars. And the time that life could have been starting on Earth about 4 billion years ago, Mars was also warm and wet, and it would have different cation concentrations based on what we know in Mars geology and geochemistry. And Dave, you can explain.
Yeah, I'm just going to take one of these. Calcium. Calcium is toxic. If you have too much calcium in a cell, that cell cannot remain alive. What she found is that calcium higher than 2.5 millimolar, keep in mind the ocean is 10 millimolar, higher than that, membranes cannot form. Then she tested all these other strips as well. And so it just shows how we can constrain our understanding of life beginning by using Urable factors.
And what she did, which was amazing, she's working on the Perseverance team as a student. She drew this line at 3.5 billion years ago in Mars history, when these concentrations, because of drying, would have been going up into this range, more dry conditions, cooler as well, and proposed that there was some period, perhaps in the Noachian or Hesperian, where perhaps it would have been impossible for protocells to self-assemble on the surface of Mars. So Mars left urability, left the ability to start life kind of early on in the history, and it's certainly at the surface today, it's inurable. It may be habitable. It may be habitable in the wet rock if life did start, but it's inurable
Yeah.
as a planet.
Okay, we're going to get up now to a new herbal factor. And that has to do with this amazing story that has just come out in the last couple of years. Three of my colleagues in the astronomy department and earth sciences at UC Santa Cruz, that's Francis Nimmo, Joel Premack, and Sandy Faber. Those three are some of our leading astronomers and earth scientists at UC Santa Cruz. And they pointed out that the uranium and thorium radioactive materials have half-lives in the range of 4 billion years. That's about as long as the Earth has been around. These are produced by collisions of neutron stars. Neutron stars, but a neutron star, by the way, is fantastic. A neutron star is not much bigger than San Jose, and yet it has the mass of the sun accumulating within that. It's basically almost a pure neutron agglomerate. So when those get together, there's an enormous amount of energy released, and these are strewn out into interstellar space and become part of the molecular clouds within which solar systems and stars emerge. So keep that in mind. The next year. One example of this is the Crab Nebula. These neutron stars are formed in a supernova explosion, and neutron stars are the remains of all of this big star, much larger than the sun. In fact, it went through a supernova, and this is the remains of it. So mixed out here are uranium and thorium and a whole bunch of other elements that have been strewn into outer space. And right in the center, so the neutron star, it's spinning 30 times per second, and you can hear it as a radio signal because that's kind of like a beam coming around. It has a buzzing sound if you hear it. So that is an example.
An
of a
early
neutron
study
star.
detection, maybe was it at Green Bank that they heard the first pulsar? It says early
No,
on in Frank's
was,
career that was something
And the
like
first
that.
was in England.
Is it England?
Yeah.
Yeah, yeah.
Right. Young woman. Somebody else got a Nobel Prize for that, as I recall. There we go. Yeah.
Okay, gotcha.
Okay, let's go a little bit further in this now. If you are a planet and you are gathering stuff from this molecular cloud from which planets accrete, you can have too much uranium and thorium that makes too much heat, and the molten aspect out here is chaotic. It doesn't have these convections that give rise to a magnetic field. This magnetic field, of course, is protective, sort of diverts a lot of hard radiation from reaching the Earth. So it can be too hot or be too cold, not enough uranium and thorium. So as a result, we have a frozen crust. You can still have a magnetic field, but you cannot have volcanic activity. See all these volcanoes exploding here, a lot of volcanic, but none here. And then you can have something just right. The title of Joel Premack's paper, from which I got these images, is Goldilocks. This is a Goldilocks planet because it has the right amount of uranium and thorium to keep the inner portion of the Earth at the right temperature to allow plate tectonics to occur and a reasonable amount of volcanic activity. And we are depending on volcanic activity to drive the chemistry of the origin of life. Okay, keep that in mind.
So the cycle that Dave alluded to at the beginning requires subaerial landscapes with little pools that are undergoing cycles, regular cycles of wetting and drying. And Dave, you can explain what happens when this occurs.
Again, this is from my research. These are experiments that we've done in the past. Here is encapsulation of nucleic acid. There's a mixture of a lipid and DNA in this case, stained with a fluorescent dye. This is what we call a protocell. Anyone in this room could make these. It's that simple. I think you'd probably just do it with a bar of soap. Soap is a fatty acid. Mix it with some DNA, put it through a single wet dry cycle, look at it under the microscope, and you're going to see this. So let that soak in. That is an easy way to get all the way up to what we call protocells. Here now is starting to dry out, and we begin to see these vesicles fusing to form what we call a multilamellar matrix. And that's down here. See all those little lines there? Those are all fused membranes that have made this multilamellar dehydrated matrix. So that leads to a cycle that we think is the way that you get up to protocells and then perhaps to evolution.
So this cycle is something in our field we call a kinetic trap, where you get these populations of quadrillions of polymers that are being synthesized in the dry phase, butted off into little compartments that they have to stabilize to survive the wet phase so they don't get disgorged into the bulk solution. They come back down, and then the surviving population of protocells with their polymers or cargoes, which go back into the dry phase to get resynthesized. And throughout this entire cycle, you have cycles of selection. It's phenotypic combinatorial selection, but we think this is an engine that can drive polymer evolution. And so out of this, you will get enormous sequence libraries starting at random and gradually out of the background, selecting polymers for functions like forming a pore to stabilize the vesicle, starting basic metabolic or catalytic processes will emerge in a system that's this large, that's undergoing selection pressures. This is selection before Darwinian selection, because there are no genes yet. Genes will emerge in such a system. And if we go on, this is some of the work we've been doing in the field that Dave alluded to. This is out at Fly Geyser in northern Nevada, right near the Burning Man site. It's during a trip that we did with the BBC about a year ago. And you can see it's in a volcanic setting. We've got our little slide tray set out there. We're taking the spring water directly from these hot springs, and we're wet dry cycling in basically open slides. And we're getting this. We're getting films of mononucleotides and actually even a little silica coming out of solution that provides a matrix. And Dave, you can take it from here.
So here's a little of the laboratory evidence I mentioned. This is the hot spring water from the Fly Geyser. We have a lipid amplifier that can make membranes, and the membranes have encapsulated RNA. So I see this under the microscope. The RNA can be made fluorescent by adding a fluorescent dye. And here you see now, this is what we call a protocell. It's not alive, but it's a big step toward life, because populations of protocells can undergo selection and evolution. A couple little bits of laboratory evidence. These are what we call HPLC, for high performance liquid chromatography. There's a column. We put our mixture into the top of the column and force it through under high pressure. And small things come out first. These are the monomers that we put in. And then out here, we see the oligomers making these peaks out here. Now we can actually see these oligomers by a technique called atomic force microscopy. Atomic force works as a tiny atomically sharp needle, and it vibrates up and down and scans a specimen. And as it scans, when it comes to something that rises above the plane, it will give a signal. And this is atomic force microscopy. And here is one of these. And it's very clear that we have aggregates of guanine monophosphate and cytosine monophosphate, and we can see these polymers growing out. These are thousands of nucleotides long. So we are making nucleic acids by a non-enzymatic process involving wet-dry cycles in the laboratory and also in places like Fly Geyser.
So putting it all together, this is from our astrobiology publication of 2 years ago. We called it a hot spring origin of life. We worked for a couple of years with colleagues to sort of shape a hypothetical landscape where we think the process of life can begin. And so we start with the solar system accretion disk. That's not Saturn. That's probably what the sun would look like. And Kepler and TESS are seeing these things, these disks that are full of organic compounds, the compounds that are coming back from the asteroid missions. And in fact, I've got one here that if I hold it up and give it a sniff, this is from the Murray meteorite. And we just ground up a little bit of powder from the interior and dried it down in a buffered solution. And you can smell the polycyclic aromatic hydrocarbons that are 4.6 billion years old.
Imagine smelling something older than the planet Earth that was delivered to Earth in Australia in 1969. It's got an interesting, oily, dusty smell to me. We're going to pass this around. We've done this with many audiences. Nobody has been poisoned by it yet. But keep in mind that the same stuff is in cigarette smoke, polycyclic aromatic hydrocarbons. So that's what you're smelling.
So that's literally sort of the smell of space coming in, not panspermia, but the building blocks of life coming in. They will be deposited, coming through the atmosphere on dust particles and meteorites, and the atmosphere itself could have been biogenic. It could be generating abundant organics in this time period. There are a number of research groups looking at that. So this material will accumulate in these little pools on the land, but if they fall into the bulk of the ocean, they're lost. So all of that organic feedstock can't participate in prebiotic chemistry if it lands in a large volume of water. It has to land in a version of Darwin's warm little ponds where it can get concentrated. And the interesting thing about hydrothermal fields, say in a caldera environment like this, is you have all different chemistries, all different periodicities of cycling, all different temperature ranges. So all kinds of different chemistry can happen. And if you look on the left, we're getting structures forming, membranes forming. And if these materials, it's like nature's chemistry set, are feeding a pool that is being cycled, say by geyser input or other sources of hydration and dehydration, you get this cycle going in a pool. It generates what we're calling the progenote, a term that Carl Woese used back 40 years ago, which is the form that carries you from self-assembled passive things to active living microbial communities. That's the name he gave for the progenote. He predicted it would be very much horizontal sharing of gene structure because there's no vertical descent. And that's what, when I went to see George Fox at University of Houston, who's the co-author of that paper, he said, what you and Dave are generating in your little dishes, this protocell sludges, are the closest thing that Carl and I, when we talked about the progenote, the closest thing that we had in mind. So these progenote masses can be distributed. They can flow in the hydrothermal system downstream. They can be blown as dried films, the kind of proto-seeds or spores. You have a combinatorial landscape of evolution that's happening through cycling and sharing across the landscape, just as biology works today. You get adaptation to tougher environments like this estuarine environment where salt is coming in from the ocean, and then you need active ion pumps to equilibrate that salt out. And by the time you get to the ocean shore, that's an extremophile environment for early life. That's not a source environment. High tides, high saline content. Once they're adapted to the seashore, you have colonization of the entire planet. So life starting on land and then finding its way into the oceans, not the other way around. And the rock record's backing this up. This is geyserite formed by freshwater hot spring action in the Pilbara in Australia on a piece of Archean landscape discovered in 2014, and it has clear evidence for microbial life. Splashing geysers at 3.5 billion years ago. This is lacustrine stromatolite, which I have one in my hand here. This is from the Tumbiana Formation, which is a long thing about the length of Lake Malawi that's sticking up out of the Australian landscape. It's 3 billion years old, and I'll pass it around. But these little ridges are stromatolites. They're what life does when it's in a biofilm and it's getting covered by sediments. They'll cement the sediment together and grow up to keep access to the light. And that's why you get these layered structures. And this is a mudstone. You can see all the mud in here. And it's very heavy because there's a lot of iron in the earth 3 billion years ago. And this is what we're looking for on Mars with Perseverance and Curiosity and the other missions. If this was found on Mars, it would be pretty definitive. So we'll hand that around too. So just finishing this up, once you have adaptation to the marine seashore, you get these dome-like stromatolites that are much taller because they have to deal with tides fluctuation. And you get a ubiquitous fossil that pretty much is the dominant form of life for 85% of Earth's history. So what are the implications for the Drake equation, the Fermi paradox, and SETI? Well, what we suggest is that the inventory of Urable worlds, if we start looking at exoplanets as Urable or not Urable, that these are actually now can be more tightly constrained by what we've identified as 28 factors. One of them that Dave brought up just now, which is cores with uranium and thorium, not too much and not too little, is one really key factor. So if this inventory is now constrained, we can now maybe suggest, and this is something new in our field, that microbes are hard, not easy. So it's been sort of a hand-waving assumption that if you have water worlds, you kind of get microbes for free. Well, if I had a world that was completely covered with an ice shell, had no volcanism and no access to this atmosphere, air, water interface to drive all this chemistry, I'm not going to get microbes, just not. So in fact, all those water worlds, 1/3 of exoplanets actually could be taken off the table as being places where life can start in this framework. So if we're now constraining that microbes are actually hard, not easy to get started, because the chasm, the evolutionary chasm you have to pass through, it's like a swinging bridge. If you're missing one little rope section, you're going to fall. And on that swinging bridge, a passively assembled protocell is gradually getting all the technology to eventually divide itself, grow and divide itself, and pass its genes along. This is an enormous chasm. And it's a place for amazing thought experiments. But to cross through that molecular evolution chasm is non-trivial. I would predict it's as hard as the transition from single cell to multicellular life, maybe even harder. So all of that implies that perhaps intelligent life would be further constrained, and that the implication for the Fermi paradox is that the chance of detecting ETI and extraterrestrial intelligence is vanishingly small, really vanishingly small. Now, before we all sort of throw up our hands and say, well, let's close up shop here at the SETI Institute, it's not zero. So what we want to propose of our last slide here is that here's some work that we could all engage in, some really productive work. If we have a new framework that called urability, and we now have, thanks to TESS and Kepler, we have this huge inventory of exoplanets and exoworlds, and we have our colleagues doing modeled worlds, billions or trillions of worlds that they can now model. Could we apply the combinations of urable factors to these detected or modeled habitable terrestrial exoplanets? And then we can constrain our search. You could do like a taxonomy or inventory of all these planets that and suggest which ones can start life, and then which ones can carry it to complexity and intelligence. So that's different. That would require this uranium thorium core, because if we don't have ongoing volcanism, we have the Mars situation of the stagnant lid, just a little bit of volcanic activity, the loss of, because of the magnetosphere, the loss of its surface water, its atmosphere. And so you're an urable planet that then becomes a graveyard for microbiota. So in this one branch, if we have we've identified an urable world that can go to intelligence, what are those factors? Not just volcanism, of course. But if this Urable world goes, it lacks the factor of this uranium thorium core content, then it goes toward Mars. It takes that, and so complex development of life is terminated in rock-borne refuge halophilic microbes. That's the termination of evolution of those communities. So with that, I want to thank you and thank SETI and thank Frank, Rebecca, and everyone for inviting us back, and welcome back to in-person events, and thank my colleague here, Dave Deamer, and Bill Diamond.
Good.
Okay. This
So
is
to
what
stop
happens
this-
when we meet people when we have talks in person. Basically, the talk was supposed to last 15 minutes. It's
too
most
bad.
like 30 minutes, right? All right.
We try, we
We
do
try.
our best.
I have a ton of questions because I read your papers. So I'm gonna start by something a little bit very direct, you know me, I'm very direct. So you have defined some parameter, physical, chemical conditions, and even now cosmical conditions for the emergence of life on habitable planets. I'm kind of curious, are they truly universal? Can you truly say that those physical parameters for planets will work on any type of planet? Don't we like imagination, for instance? Is it possible that there is something you're missing in this theory?
My research field thrives on imagination. I'm going to quote Mark Twain. Mark Twain, in his book, Life on the Mississippi, has a character in it who commented on science. And the comment was the following: science is fascinating. One gets such a vast return of conjecture from such a minute investment of fact.
Mm-hmm.
So that is really a lot of the original life field is like that. Huge conjecture using imagination. That's fun. We like to do that. We like to have ideas. We like to tell people about it. But I have that one more step in me as an experimentalist, that I want ideas that are testable.
Mm-hmm.
So you brought up a possibility. I can imagine something as you suggested, but I would then say, how am I going to test my imagination? So that's just the way I happen to work.
Okay. You want to add something? You good? All right. We talk about urability, the concept. I would like you to go into more details for some solar system bodies. So can you tell us about whether or not Mars is urable?
Mars was urable by all that we know about it. It had volcanoes, it had shallow liquid water seas, but only for about 500 million years, say, before it began to evaporate. As it evaporated, it became increasingly inurable, and the organisms probably were able to adapt to the increasing salinity, just as halophilic organisms do today on this Earth. But at some point, they give up because liquid water disappears from the surface. And at that point, at least the surface became inurable. We don't know enough yet about the underlying surface. We're going to have to drill down. But I would not be surprised if we find evidence for maybe extinct microbial life and maybe some robust survivors. That'd be wonderful if that happens. Yeah.
So in the case of the icy moons in our article in astrobiology, the Enceladus, for example, only had 6 factors of the 28. It certainly has liquid water. It has potentially a hydrothermal system operating at the rock-water interface, but that's actually disputed. It's not known for sure that it could be cracking and pressure building up that is creating the geyser system that comes out of Enceladus and Europa. So it's not quite sure, because if you have a plume, basically a hydrothermal vent on Enceladus, it's just going to get absorbed in the ocean. It's many, it's 100, 200 kilometers to that ice region. And the question being, one of our colleagues at a conference, that the energy sources available, that there's no sunlight energy available on icy moons. And that the energy that's available that is geothermal or geochemical is 6 orders of magnitude lower than even the Earth systems. So you're talking about really small amounts of energy. So if Enceladus or Europa got impacted by, say, a Mars meteorite that had bugs in it, or Earth meteorite, and they got in there, they would not much to eat there. There's no McDonald's there. There's no free lunch there. So it's a really extremophile environment for even Earth life to survive at such temperatures as well. So what we're arguing is that those worlds are inurable. They may be habitable, but they also may be sterile. And future missions to sample those plumes, even surface missions, may give us some answers. But at NASA meetings, we're sort of the guys in the room that are saying, don't think it's going to be life there. There has to be, someone in the opposition.
Anyway. And what about Titan?
Titan, oh boy. Yeah, Titan, very cold. So there might be a layer of liquid water, I hear, a little bit under the icy surface, but it is really very cold. There's something called activation energy. Every chemical reaction has to have a sort of a hurdle to jump over called activation energy before it can go on to complete the reaction. Icy cold at the temperatures of Titan, very little activation energy available. The energy that is available is sunlight hitting the upper atmosphere and causing certain carbon nitrogen molecules to polymerize. So there are polymers there, but there are not polymers that can be turned over. In our bodies and in life on Earth, everything is turning over all the time because you can take water away from monomers to get polymers. You can put the water back and get the monomers back. That's called digestion. Okay, so that cannot happen with these Titan polymers. They're kind of stuck.
All right, so it's snowing totally, but nothing is happening.
Yeah.
It's like a world which does not interact. There's no interaction, no destruction, and apparently alteration is important to create these complex molecules.
Mm-hmm.
I just want to mention that if you have any questions in the audience, we're gonna give you some piece of paper. There is a better word to say, and you can write them down and you can give them to Beth over there, and she will select some of them. We're not gonna be able to take all the questions, but our speakers will stay 5 more minutes and we answer to all your questions later on. So let's talk about water. That's a very anthropocentric view here. You have been mentioning that we need water to create these membrane molecules. We need water. We need a wet-dry cycle to create these complex molecules. So does that mean that water is a requirement for life?
Yes.
Okay.
Nice short answer.
So no water, no life.
Yep.
Okay. Good. I'm not going to challenge you on this one because I want to go through some of my questions. Something not really about science, but I like to ask questions about how we do the science, how this idea of urability comes from. What's the story here?
Yeah, I have been comparing seawater with freshwater for the last 20 years. And I had this intuition that it's going to be biophysically limiting to have all those salts in the salty ocean. Now, people had assumed that life began in the ocean because 99% of all the water on Earth is in the ocean. Just 1%, less than 1%, is actually fresh water. Most of that is Antarctic and Greenland ice, of course. But there's a little bit that falls as precipitation. And I said, okay, give me that. That's distilled water. That's what I use in the laboratory. And therefore, the weight of evidence, again, supports the assumption that a hot spring is a more conducive place to explore in terms of the origin of life than a biophysically problematic seawater environment that does not have the wet-dry cycles. The wet-dry cycles really do add chemical energy and cause things to happen that cannot happen in solution. So chemists have to get used to that, by the way. They don't like dry stuff out. Oh, you just get a mess. They say, you'll make tar. Well, I say, try it out. Some of them have. And we're starting to see papers now. Wet dry cycles does this, wet dry cycles do that. So the idea is catching on. And it's not just wet and dry. It's wet, dry, wet, dry, wet, dry, wet, dry, wet, dry. We have a colleague in Canada that ran 200 wet dry cycles in a special device they have. So that allows things to happen and to build. Let me just give you this as my last comment here. The first cycle with pure monomers, we know will make some polymers. Those polymers now are present as templates. Suddenly something is new. We have a template that can guide the synthesis of the next set of polymers. And that's what we're doing in the laboratory right now. We're seeing if we can transfer a sequence of bases from a template DNA into a product DNA that is lined up on that template and then linked up into a polymer. We can do that because we have nanopore sequencing. We can look at the sequence of a single molecule of DNA. And if that sequence is there, we're going to see it.
And Frank, I can give you the exact moment when we came up with the word.
I wanted to hear this.
So with all that as background, we're watching the SETI broadcast for the Mars 2020 Perseverance landing. You know, the SETI event, we were actually speakers. And David came over to my Gandalf house in the Santa Cruz Mountains, and he had this word in his head, which was, well, they talk about Mars being habitable, but then maybe life could start. And the colleagues are sort of struggling with, well, there's early conditions which life can start, and then there's the current conditions where it's still habitable. And we realized that they needed a new term, and Dave came up with the term origin ability. And it was just a huge mouthful. We just get an origin ability. And about 2 weeks later, he wrote and said, I've got it. Urability, because Ur is a German root term for soonest and earliest. Remember Ur, the city in Sumeria, the first city in the Ur continent, and Urschleim, Ernst Haeckel's idea of the origin of all things. And so that's when it was born, around the beginning of COVID, around April of 2020.
Yeah.
Yeah.
All right. So that's when we invited you to speak at the Mars 2020 Perseverance landing.
Yes, it came from
So
that.
Bess is a part of this urability invention.
It came from that time. Yeah.
Great, thank you. We mentioned at the end of your presentation exoplanets, and you know I love exoplanets for multiple reasons because there's thousands of them, and I think that's where we're gonna find life in our universe. Can you tell us what kind of phenomena we will need to be able to see or to measure on an exoplanet to say whether or not this exoplanet is urable?
Yeah, I had lunch with a whole team, a whole slew of exoplanet people about 6 years ago at a NASA. They had their review panels for grants, and I'd never met an exoplanet person. They'd never met an origins person, and we just started to talk. And they said, "Well, so what you're saying is what we need to look for on our exoplanets are glints." And I said, "What's a glint?" And they said, "Well, we think we can see that there's surface water on a planet. We get these like spectra that show that a glint." I said, "Sure, and maybe we need to be able to detect if there's landscapes, and maybe also volcanism that's affecting the atmosphere." And I sort of thought at the time, and as the planet tidally locked to its star, we're getting wet dry, we're getting diurnal cycles, and we sort of came up with that at the meeting. It's like, if we can see those things, we can see a world that is dynamically potential to start life, and perhaps that we know it's a young world, not an old world. Or we can even look at solar system accretion disks and predict that those worlds might become urable as they form. So that was the beginnings. But this is brand new. It's a brand new connection between communities, and hopefully future missions could detect if volcanism is present, could detect glints, I think we're talking about that earlier.
Yeah,
Yeah.
there will be telescopes, space telescope to do these kind of things in 2040. So we will talk about this in 2045. The detection of urable planets. We're gonna take a few questions very soon. I have one last question, something I read in the paper that I really like, is this concept of one-shot urability. So this idea that when life appears on a planet, basically no other genesis could appear later on. Can you elaborate a bit about that and tell us where this is coming from?
It goes back to Charles Darwin's little end of his sentence about the warm little pond, that life can't start today because it would be consumed. So Earth today, unless we do it in a sterile laboratory simulator that doesn't allow E. coli and other bugs in, it's just going to get eaten by the extant biology. Our simple little flabby lipid protocells and our wonderful little RNA is food. It's nutrients for life. So it's just going to get gobbled up. And of course, you know, we know that there's one genetic code across all life on Earth, across all organisms. There's one PTC tunnel in the ribosome. You know, it's really a common core. Of course, in the beginning, there may have been sort of multiple starts. There may have been sort of weird failures that then merged into the bushy tree of life. And there may not be a trunk in that tree of life. But that's all speculation as to how did that common core emerge. Because we've never found something that's truly alien, that's not using this common operating system.
Okay. We have a lot of questions. I don't know how I'm gonna do this. So we're gonna play the game where I ask the questions and you give me a less than 10 seconds answer. Is that okay? All right. First question. How likely do you think it is that life elsewhere will have RNA or DNA or something very close to it?
The answer is yes.
So you do believe that
No,
this
no,
is the ultimate
no, it's a
molecule?
good question. It's a good question.
All right.
With somebody here at NASA Ames, Winona Birkacher, former grad student with us, I have just put a grant proposal in. We're going to look not for DNA as a life detection that is like our DNA, but we're going to be looking for a polyanion that is a generalized backbone of DNA and RNA. So we expect it to be different. If we find life on Mars, we expect it to be different from what we do here if it was a separate origin. But it's the same, then we might all be Martians. It may have started on Mars and been delivered to the Earth. Now that's something to think about.
Something to think about tonight before going to bed. Bruce, 10 seconds. How important is a magnetic field for urability?
It's very important because without it, you get your atmosphere stripped away and you get the complete sterilization and the dehydration of the surface. And you're basically then exposed to the elements. And so you can't get your chemistry going. You lose all liquid water on the surface. It's your protection's gone.
Okay, thank you. Dave, how long did salinity stay low enough to allow lipid formation in the early ocean? So there's a question.
Oh,
about
yeah,
salt.
got it.
Yeah.
Okay. Paul Knauf, I think University of Arizona or Arizona State, was able to show and calculate that the ocean back when life began was probably as salty and even saltier than today's ocean. He took all of the mineral salt deposits, dissolved them back in the ocean, and they came from the ocean. And of course, you get more than what it is now, because so much of it is turned into mineral salt.
And the ocean was full of dissolved iron. It would have been sort of coffee colored, you know, full of a lot of things that had to be precipitated out.
Okay. I have so many. I need to decide here. Is a configuration like our own Earth moon system optimal for urable world?
Well, do we need a large moon? like
Yeah,
we
that's
have?
right. There is speculation that maybe our large moon, the largest in relation to the Earth's mass of any planets in the solar system, might have had some favorable effect, but I don't think that's an essential parameter, something we have to consider, because life is nanoscopic, and we really have to understand the chemistry of life to understand how it could begin.
Okay. I like this one, but it's for an astronomer, but I'm trying this one. In your opinion, are planets around highly active stars, which produce X-ray flares and so on, urable under special circumstances?
I mean, I think there's a lot of literature now, say on the TRAPPIST-1 system, that shows that these flares could be, highly deleterious to living systems getting started or persisting on those worlds.
Is there a way to go around that?
Hide. A lot of life gets
Right.
way down there.
Okay, so remember that, microbes. If
Yeah.
you're nearby M dwarf and it's very active, you hide.
Mhm.
Okay. Is there, I'm gonna keep those questions for my last one.
Questions in the room?
They are here too, right?
They're here too.
Yeah.
Okay.
So is your work the real reason for the so-called great filter?
We're not really experts in any of that, really any big SETI questions, but I think that what we're trying to do is provide a workable framework that you can actually test not only in Earth environments, to test it out chemically, but actually go back in the rock record. And because in a sense, we're not really guessing. A lot of our colleagues have said in the past, well, it's only a guess of what the conditions were at the time of the origin of life. It's not a guess anymore. We have those rocks in Australia that are only 500 million years or so past the putative origin point. Our colleagues did drill core samples in the summer of 2018. When they brought them up, they found hot spring facies, and they found all the elements needed that have been identified, such as boron. In that environment, they found the chemical compositions, the atmosphere composition, the ocean and freshwater composition is known from 3.5 billion years ago. And we have meteoritic infall. We know what that material is that was coming in. So is it really guesswork? So what we can do is we can try it out in simulation chambers, try to simulate the early Earth with really informed guesses, and then go into hot spring environments and try it out. And since the chemistry and physics are the same, presumably now, as they were 4 billion years ago, we can really give good constraints on where and how life can begin.
Okay, that's a very good transition for my question, my last question. So let's play again another game. I give you 1 million years of life, an infinite budget. Okay, and I tell you, your work is going to design the perfect experiment to prove or disprove the concept of urability. What would you do?
Well, first I would build on the foundation that we have so far, which is that we can get all the way up to what we call protocells. And we do that non-enzymatically. These are all just purely biophysical and chemical processes. And we get nucleic acids, things like nucleic acids. They're not exactly like it, but they would be defined chemically as nucleic acids. And they're in a membrane that has self-assembled and captured this. So the obvious next question is to add function. What functions can we select for in those polymers that would make them more robust, step toward the first forms of life? And the most important function that we're working on now is replication. Life is best defined as a system of molecules that can make more of itself by polymerizing monomers into polymers, and that's a guided process by genes, okay? So that's sort of a simple description of life. So we want to take the very next step, and it would cost a lot of money. I'm glad you're giving me infinite amounts, because I want to see if we can get a non-enzymatic replication, and that's what we're trying to do right now, because we have nanopore sequencing available to us. No other sequencing could do this experiment I described.
And so literally we're starting in January with a whole new research program for the next 12 months on this. But give us $10 million and consider a machine sort of like the 21st century cyclotron. So cyclotrons in the 20th century allowed us to see into the very small in physics, to smash atoms and look at subatomic structure. What about a cyclotron for biology? A machine that we talked about to our colleagues in Australia, and they applied for $10 million for it, but didn't receive it. It's a chamber like about this big, and it has literally a hot spring in it. It has little injectors. It has hot spring minerals for the mineral involvement. It has ways to cycle in and out. It simulates that hydrothermal field at small scale. It will be tens of trillions of protocells circulating there. It'll be thousands of millions of cycles that they can do. They can rock the whole system back and forth. They get wet-dry cycling. And then out come the protocells down little cell sorting tubes, protocell sorting tubes, and they get branched off. Do they contain polymers or not? Then they go into one of your nanopore sequencers. We break them up and we look for the strings. And then the test would be if we start to see in one of the little pools in there, the mass of protocells suddenly grows. Something's going on. There's a template that's made a copy of a thing that's made more peptides, which made the protocells more stable, which make more of them form. It looks like there's growth happening here. We sequence that in real time and find the template that emerged spontaneously that made that peptide over and over and over and over again. Then what we do is we hit it with higher ultraviolet to break those bonds, to subject it to stress, which would have been around on the early Earth. And we watch the system crash, but not all the way to zero. And we keep cycling it with the same conditions. And if the system responds and grows back, like life would do, we sequence it again and we find a new template that has emerged through selection that's making a different peptide that's providing different protection and different response. Now we have a system that is doing what life does. It's not alive yet, but it's doing all the things that life would do, but not even with distinct cells that divide on their own, because they can bud. They can go through these selections. They have sources of energy and they have templating, and it's an artificial evolution, but it's in chemistry in the lab. It's not in just computer simulation. I think that will be convincing. And I'm predicting that that ignoble sludge will win the Nobel Prize even. And that it will be powerful for humanity to see that growing thing that grew back, because it will be like seeing the Earth from Apollo 8. That's potentially our ancestor. That's the process that made us right there. And it could be demonstrated in a decade in a laboratory somewhere.
Yeah. So what about creating life? At which moment you're gonna say what I'm seeing here is life? What's gonna be the criteria for this experiment?
So we're predicting that as we go into this chasm, where we get a little lifelike property going, we could actually have a competition. I talked about this with Richard Dawkins back 20-some years ago. Could we have an international competition where teams try to create more lifelike systems? And then they're adjudicated every year. So if a team showed the spontaneous emergence of a pore that got templated and it was replicating throughout the system, as our colleagues have done in Germany for the first time, then they would win the origin of the Genesis Prize for that year. And we just keep pushing the bar. And we can use synthetic biology on the side. We can literally, and this is what our colleagues at Harvard are doing in other labs. They're using synthetic biology to make a little enzyme that they know is going to cause a replication step within a protocell. They're just injecting it, and they're watching how it works through a population. So you can use either from de novo random sequencing, which might take too long, well beyond a graduate student's lifetime, beyond it, or you can use synthetic biology to say it is likely that this 55-mer peptide or RNA could emerge from a random sequence and be selected. So we're just going to put it in and see what it does. And the thing is, it's a black box, so it's way too complex to compute in simulation. You just have to build the systems and try them and see where they go. And then to actually know what they're doing, it's a kind of SETI, actually. This came up at the Contact Conference like 20 years ago. If we try to do artificial life, wet artificial life, and we try to detect that it has a certain amount of aliveness, it's a type of SETI, but it's down the barrel of our microscope, not through our telescopes. And so that's something to think about.
All right, thank you very much. We have a lot to process tonight. Thank you, Dave and Bruce, for participating to this experiment.
Our pleasure.
A virtual, in-person SETI
Yeah.
talk. Really
Great.
nice to talk to you.
We'll remember this night.
Thank you, Frank, for bringing it all back.
Thank you.
Fantastic. We'll try, since those of you who are here in person have the unique opportunity to actually capture these two gentlemen before they head off to bed. Some of you may be able to ask your questions to them, and we're sorry we couldn't get to all the questions. The thing is, this is such a fascinating topic. It generated loads of questions. I will confess, the only reason I actually became the CEO of the SETI Institute is so I would get to ask a question no matter what. So, so one thing I wanted you to comment on, because you mentioned this a couple of times, and I wanted to give everybody sort of an appreciation for how important this is. But you talked about the formation of membranes and how important membranes are and the conditions under which they can or cannot form and why that matters. So maybe just a short little treatise on membranes would be interesting.
Everybody in this room has made membranes. As children, we have blown soap bubbles. A soap bubble is a membrane composed of the sorts of molecules we think were available on the prebiotic earth. If you would look at a soap solution under the microscope, as I have, you would discover lots of microscopic bubbles. Soap is a fatty acid that self-assembles all by itself. Nothing tells it to do this except the laws of physics. It self-assembles into compartments that you can see. Those compartments can capture polymers. We've done it. Any of you could do it if you want to try it out yourself. Very simple. Soap plus DNA, dry it out, put some water back in, look at it under the microscope. You'll discover that you have made protocells. We did this for the first time back in the 1980s, but only recently have we begun to realize that this is important for the origin of life, as well as just capturing stuff in the bubble and membrane. So that is, I think, an answer to what you want to know more about.
Yeah, I mean, the walls of the cell, right,
Self-assembly
are a
and
membrane.
Every one of your 37 trillion cells in your body, that's the latest count, has a self-assembled membrane. It's phospholipid, which is two fatty acid chains attached to a phosphate. So it's that simple.
And one thing to add to it, from a geeky computer person's perspective, when I look at Dave's membrane, they're moving around, they're sliding past each other. They go from sheets to compartments to tubes to, it's like it's alive, but it's just a lipid fatty acid membrane. When you see the dynamics of that system and you imagine that polymers could be affixed to those membranes or sliding between them, it's a massive networked highway system. What we're seeing in the Fly Geyser, that one experiment, is a system so complex, it actually is more complex than the planet it lies upon by the number of objects, distinct objects, and the number of encounters that those things are doing, moving around on membranes. It's a large Conway's game of life. You know, remember from way back in the 60s, when a computer guy, I looked at that, I said, this is a combinatorial machine for the encountering of seemingly almost miraculous functions that will emerge from this machine. And it's a matrix that will preserve them and propagate them, just like an A-Life program, just like viruses on the internet. And that's potentially a new idea that life started as a networked system, a communal network system of sharing and nodes, not as a spherical individual thing competing with other spherical individual things called cells. It's a brand new idea.
Does Dave know that you're looking at his membranes, or you do this without, when he's not looking?
I sneak into
You
the
sneak
lab.
Excellent. Okay, the second and final sort of question / observation is you describe the oceans because of the various high concentrations of chloride compounds as being not urable. And yet life, once it emerges and evolves, adapts, and can in fact thrive in these environments which are not urable. So can you comment on this adaptability, how we go from a non-urable environment to one that can nevertheless support life once it emerges and
Sure.
takes hold.
One of the things that all life does is to pump ions in our membranes. There's little enzymes that can exchange ions using energy to do that. So our cells pump calcium out. I told you calcium is toxic. It gets above in the millimolar range, the cell is a goner. So calcium is pumped out. Magnesium, however, stays in. Magnesium gets up about 5 millimolar, still only a tenth of the ocean, but it is necessary to a lot of the stuff that goes on in cells. Now, sodium and potassium are the other two ions. Potassium is pumped in, sodium is pumped out. That lets us have a nervous system. So if you want to have intelligent life, you better have a nervous system that can pump sodium and potassium across the membrane and maintain their gradient, because that's how we communicate down our axons from a live nerve cell.
Fantastic. Well, did you want?
So Armin Mulkajenian in a PNAS paper about 10 years ago made that argument that because life has to have active ion pumps, that if you have it in seawater and you didn't have that active ion pumps, you'd be extinguished really quickly. So he argued that life cannot start in the ocean because it's a catch-22, you need an ion pump. And so he argued it involved a anoxic subaerial spring environments.
Fantastic. So obviously, again, we're out of time. We've gone a little over time. Thank you for your patience, and thanks to those of you online for listening and being with us tonight. The first thing I want to do is thank you in the official and formal and traditional manner that we do for our SETI Talk guests, where you are the recipients of the rare, perhaps more rare than life itself, SETI Talks mug and patch.
What about me?
Yes, there's two.
Thank you.
Yes, and
That's not all.
these fetch millions on eBay, so keep that in mind. That's how rare they are. But thank you both very much for an extraordinary talk. And I would say, Steve, I think we should talk about, if all we need to do is raise 10 million to create an origins of life machine and create life itself, we can add a Stein to the back of your name, so you become Damerstein and Deamerstein. And we 10 million for a life generation machine. We should do it.
Yeah.
We should make it happen. Anyway,
We can work together on that.
I think we should. I think we should. So let me do some formal closing remarks. So again, thank you, Bruce and David and Frank, for an amazing, enlightening conversation. And thanks to all of you out there and for your great questions. Again, I'm sorry we couldn't get to all of them. But one nice thing about having questions is if you have a question that we didn't get time to address, see what you can do to find the answer on your own. Do some homework. And then, if you had a wonderful question, you came up with your own answer, let us know, write to us and tell us what happened. But I also want to let everybody know that, again, as we've done traditionally, particularly during the COVID shutdown, when we've been entirely virtual, we reached a global audience again, some of whom stayed up quite late to be with us. So we've had friends watching here tonight from New Zealand, from Canada, from Brazil, from Colombia, from Austria, India, France, and Italy. So amazing to have all of you with us again tonight. And thank you so much for doing that. Just want to also remind you all that the SETI Talks program is a production of the SETI Institute in Mountain View. We're a nonprofit research and education institute whose mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and to share this knowledge with the world. Our SETI Talks lecture series is supported in part by donations from the public, from friends of science like you. We bring these lectures and other events to you at no cost, but we're very grateful for any and all donations that allow us to continue bringing you stories of extraordinary science and exploration. You can visit us at SETI.org to learn more, and you can sign up for our monthly science newsletter, again, we call Journey. You can make a donation if you're so inclined, or at the very least, peruse our website to learn about the wide-ranging and extraordinary work we do every day to answer one of science's most profound questions: are we alone in the universe? Thanks again for all of you for being with us tonight. Thanks for our moderator, Frank. Again, our speakers and guests, David and Bruce. I want to thank Rebecca and Lee and Beth and Jasmine for all the work behind the scenes that make these SETI talks possible. Remember, the work we do at the SETI Institute is for all of humankind. Don't just stand by and watch. Come and join us at SETI.org and get involved. The search for life beyond Earth is a journey of ultimate discovery, and we invite you all to come along. Thanks for being with us. Please join us again in December for that amazing Space Telescope Science Institute meeting about JWST. We'll see you next time. We're going to have Dave and Bruce back for more of this, because this is just too fascinating to stop here tonight. Thanks again, and we'll see you next time.
You'll be killed if you return.
I'm warning you to watch your comments. Our country is a peace-loving democracy.
Of course it is.
The window! Shoot! I don't believe it. Thermoptic camouflage.